it has a drop-down menu, and it's saying use Riemann sums with a lower estimate. And so what that means is from -3 to 3, that's what we call our full interval. Okay, so we're looking at the area underneath the curve of this y equals x squared from -3 to 3 between the x-axis and the parabola. And so if I were to look at just the subinterval, the -3 to -2 first, I'll notice that the width of each one of the rectangles is 1. Okay, and that is also happens to be the length of the subinterval. Okay, and then now if I wanted a lower estimate, what that means is, can you draw a rectangle between -3 and 2 such that the rectangle falls below the curve and it's an underestimation of the area? So the area would include all of this as well, but we can see that it's an underestimate because it falls below the curve and it doesn't estimate this area right here. Okay, so can I have you guys with your finger trace from -2, the right endpoint of the interval is -2. If I go up to here, this is the y value at y equals x squared. Okay, it's the y value, and that y value also represents the height of your rectangle. Okay, so here we have an underestimation. Over here, we also have an underestimation. So here's what happens. Go to -3. If I asked you guys to find the height at -3, you would go up to where it hits the curve and then see that it's 9. And if I were to draw a rectangle with that height between -3 and 2, would that rectangle be an over and under approximation of the area underneath the curve? Would it be an over or under approximation? Okay, so we can see that that rectangle right there would be an over approximation. It would overestimate all of this, wouldn't be actually part of the area, but it would overestimate it. And so they said just go through each subinterval and find the lower estimate of it. And so you guys can see between -1 and 0, in theory, there's a rectangle there. So if I were to pick the left endpoint, the rectangle from -1 would have led me to conclude that that's an overestimate. So they chose 0. And 0 has, for y equals x squared, the y value is 0. So that's why the height is technically 0 here. It's 0 here because the left endpoint is an underestimation. And then over here, now we see that instead of 2 being chosen, we picked 1 because the y value for 1 would lead me to a rectangle that is an under approximation. And again, this is what the lower means. It means choose rectangles that have an underestimate for the area, the approximation of the area. Okay, so now I want you guys to see what happened, what changed. Okay, if the specification in the directions say choose so that it's a upper estimation, you guys can see that same subinterval, -3 to 2, -2, but instead of this time choosing -2 as the height of the function, they chose -3, and that's going to give us a y value that's the height of the rectangle, which would then overestimate the area. And this, all of this is an error, right? This is an over approximation of the actual area underneath the curve. Do you guys follow so far what is being done here? The explanation between the lower and upper estimate. Any questions so far? Yes, no, are you guys doing okay? Okay, thank you for the feedback. And normally we are going to do an example with a lower and upper estimate as our example that we'll start with the next class. But the majority of questions are going to ask you guys for, instead of lower, upper, left Riemann sum, right Riemann sum, and midpoint Riemann sum. Okay, so what does that mean? So when I selected left, here's what happened. On the subinterval from -3 to -2, this time they're saying specifically choose -3, which is the left endpoint of my subinterval. So if I choose -3, the y value is then 9. And then if I choose -2, the y value is 4, -1, the y value is 1. If I choose the left endpoint of the subinterval from 0 to 1, I can see it's 0. If I choose 1, it's 1. If I choose 2, it's 4. So the rectangles, the height of the rectangles are all determined by the left x value of your subinterval, which would then lead you guys to find the y value of that corresponding x value. Okay, so now let's shift it to right. Oh, and just a note. Okay, this left side, you guys see the triangles or the rectangles are an overestimation This side, it's an underestimation. And over here on the right where it says Riemann sum, right now your Riemann sum is, if I were to sum up the areas of those rectangles, would give me 19. We're going to talk about how this is an exact area eventually, but right now it's only one off. That's pretty good. Just using 6 rectangles, I can come up with an area of the area underneath the curve that's only 1 unit apart from the actual area. Okay, and then here's the right endpoint. Can you guys trace with your fingers? Just give you guys a few seconds. Can you trace with your fingers? Make sure you understand where the y values of the right Riemann sum comes from, and type into the chat if that makes sense to you guys, yes or no, where those y values come from. Okay, before I move on. And you guys, 100% of this is visualization, because if I ever have questions on Riemann sums, it's always like, wait, what is this again? How do I get the y values? How do I get the height? And so it's really important that you understand this visual. So the y value again is the right endpoint. Okay, so the hardest one that I think for students to picture is not left and right, but the midpoint one. And the midpoint one is we're still using the same subinterval. So 1 is still the length, the width of each rectangle, but instead of the left and the right determining the height of your function, it's the midpoint. So here at -2.5, the y value at -2.5 is going to determine your height of your rectangle. And you guys can see that even just within this rectangle, do you see how here it's an under approximation, but here it's an over approximation? So that kind of like negates each other out or cancels each other out so that it becomes a more accurate reflection. So same thing happens here. This triangular part that was an underestimation is overshadowed by this over approximation. So together they negate, and it becomes a little bit better of approximation. So if you guys look over on the right, the area using midpoint is 17.5, the actual is 18. So we come just within a half unit, and that's pretty neat. I mean, to think that we can just use 6 rectangles and be able to approximate the area so that it's that close. So of course, when we think of this and we think of calculus and we think of limits, what do you guys think? How many rectangles do you think we can use to then come up with the actual area? If in theory, how many rectangles do you guys think we would need to come up with the actual? Okay, good, Brandon. Okay, we've studied now the entire semester about the idea of infinity, right? An infinite number of rectangles. So if I go down below, this little bar right here allows me to change it so that I can increase the number of rectangles. So you guys can see as I increase the number of rectangles all the way to 20, the discussion then becomes, I can clearly see that these rectangles mimic more of the curve than say, look at 1. Okay, so like if you only had 1, that does not really mimic it. But as you guys increase it, it starts to mimic the curve a little bit until ideally we get to infinity. Okay, so, and if I look over on the right, if you guys follow the Riemann sum tracker versus the exact interval, do you see how it increases, the Riemann sum increases in value closer and closer to 18. And with just 20 rectangles, we see that we're within, we're so close to the actual area itself, which is really, really neat. And we do this as a project at the end of the year where you guys see what does 50 do, 150, 200, and we see we get really, really close to the actual area and eventually volume as well. The right and left endpoint again determines, so let me decrease this to, oops, that changes the interval. That just determines, yes, it's like taking a limit. It's beautiful, really, if you guys think about it. And it is, the limit does come into play. But the left, someone just asked what's the left. So let me go back to the left. The left is if on the subinterval, you would pick the left x value, go up to the y value, and then that's going to determine the height. For the right one, you would pick the right endpoint and then go up to the right endpoint of your subinterval, and that's going to determine the height. So let's do this together as a problem that you guys would see on your homework assignment. So let me share. Can you guys go to page 5 now? Okay, on page 5, they want us to estimate the area underneath the curve of f of x equals e to the negative x on the interval from 0 to 2 using 4 subintervals, using right, left, midpoint rectangular approximation. So really quickly, if I can have you guys sketch e to the negative x, we know that e to the negative x is reflected across the y-axis, and it's an exponential function. So at -1, it's about 2.71. At 1, it's about a third, and then it gets closer and closer to the x-axis. That's supposed to be closer and closer. Sorry, that does not look very smooth there, but e to the negative x. Okay, so if this is from 0 to 2 and I have so much space, what I'm going to do, and it helps with you guys first seeing this for the first time, I'm going to jump by 0.25 to get, wait, no, I'm going to jump by 0.5. So let's make this, oops, let's make this 1, and let's make this 2, so it all fits onto the curve. Okay, and I'm going to talk to you guys really quickly about what this all means. Okay, we're going to label the interval 0 to 2 as A and B. And then the 4 subintervals simply means that they want you guys to have, that's the number of rectangles they want you guys to have. And we're going to assign a variable of n to it. Okay, so it's really quick. If I didn't have a formula tied to this and I tell you guys to go back to the picture, and though I purposely did it spaced out this way, if I looked at the 0 to 2, if I were to have 4 rectangles in there, what's the subinterval length, or what's the width of the rectangle? Can you guys type it into the chat? What do you think the width of the rectangle would be, so such that you would have 4 rectangles between 0 and 2? Okay, so visualizing that is important too, and you guys just all typed in 0.5. Okay, sometimes it's not so easy to come up with, and I kind of set that problem up so you guys could see the 0.5. So some people like a formula tied to it, and the formula is important as well because we'll get to other parts that include that type of formula. So in using A, B, and N, you guys can think of the subinterval length. The subinterval length is also the width of the rectangle. And we can come up with it visually looking at it, or if you guys want a formula tied to it, the change of x is what we call the subinterval length. Okay, so that's the symbol for it, delta change in x. Okay, and so we can find that by finding out, well, what is the actual length of the entire interval? And that is 2. We can come up with 2 also by taking 2 minus 0, or b minus a, and dividing it by the number of rectangles or the number of subintervals that was given, which is n. Okay, so the for this particular problem, it would be 2 minus 0 divided by 4. So therefore, each one of my rectangles will have a width of 0.5. And so if I'm coming up with the part A, it's asking for right. I know that for all 4 of my rectangles will have a width. So we think of this as the area of a rectangle as length times width, but each one of the widths of the rectangles is 0.5. So technically I can just simply factor out the 0.5 because I know every single, if I'm summing up 4 rectangles, all 4 rectangles are going to have 0.5 to it because that's the fixed width of the subinterval. Okay, and then the height of the function is determined by the y value of whatever they specified. So if they say right, I'm going to look at, now I want you guys to focus in on 0 to 0.5. Okay, that's going to be where my first rectangle goes. Okay, and I'm going to find the y value associated with the right endpoint of that subinterval, which in this case happens to be 0.5. So f of 0.5 is going to give me the height of my rectangle. So if you guys want to sketch in there what that means for that first one, it means that this is going to be my rectangle right there. The right endpoint is at 0.5, f of 0.5. Okay, and it's pretty simple after that. What you guys would do is then, okay, well, each rectangle is a half a unit apart. So the next value would be f of 1. 0.5 plus 0.5 is 1. And then I keep going, f of 1.5, and then f of 2. Okay, one way to keep track of things is there's supposed to be 4 rectangles. So it's 1, 2, 3, 4 rectangles. And if it's on a free response, you guys would just write out what those y values are with the 0.5 plugged in without having to simplify it, because that's considered algebraic. So f of negative 0.5, e of negative 1, e of 1.5, negative 1.5, and e of negative 2. And all I'm doing is plugging the corresponding x value into the f of x function to come up with the y value. And again, these represent so this represents the width, and each one of these are the heights. Or I guess you can think of it as length. Okay, so yes or no, you guys, in the chat, yes or no, if I switch my thinking for part B to left endpoint, does the width of my rectangle change? Does the subinterval change? Yes or no? Good, you guys. No, it doesn't change. So we still keep the 0.5. And can I have you guys now type into the chat, what is your first y value? What is it if f of something? Okay, and this time I'm doing left endpoint. F of, good. F of 0. Good, so that's 1. And then I'm jumping by 0.5s. F of 0.5, kind of glance over to your graph. Does that make sense to me? F of 0, then F of 0.5, then F of 1, and I'm just simply incrementing. And notice that I stopped short of 2 because, again, I'm using the left endpoint. Okay, F of 0, F of 0.5, F of 1, and F of 1.5 gives me 1, 2, 3, 4 rectangles. And then lastly, if it's algebraic simplification, you don't have to provide it. So in that spirit, I'm going to put e to the negative 0, e to the negative 1.5, or sorry, e to the negative 0.5, e to the negative 1, and then e to the negative 1.5. All right, so yes or no, you guys, for the midpoint, do you guys think that the subinterval for the midpoint changes? Does the subinterval for the midpoint change? So when we say left, right, and midpoint, those just determine your y values. Okay, your subinterval, your width is still the same. We're still looking at the same subinterval. So in this case, it's still 0.5. What do you guys think the first height of your function is? F of what would be the midpoint of your first subinterval? Good. Those of you guys typing it out. Very nice. Okay, so f of 0.25, and then jump by 0.5s from there. F of 0.75, f of 1.25, and then f of 1.75. And that gives me 1, 2, 3, 4 rectangles. And then finish it off by plugging it in to get your y values. And that's it, you guys. So we leave our answers as such. If it's free response, you guys don't have to simplify that out. Okay, as the last problem, I wanted to make sure we could get to this problem. This is going to ask us to only do the left Riemann sum, and most of the times it's just one of those. It's either left, right, or midpoint. They don't usually have you guys do all of them. So approximate the area underneath the curve of sine of x using left Riemann sums, 6 subintervals on the closed interval from 0 to 3 power 2. Just to space things out apart a little bit, I'm going to have us make this 2 units over for the x, pi over 2. And let's jump by pi over 2. So this is pi. And then we're going to go off the grid a little bit, and that is going to be 3 pi over 2. And again, just to stretch this out a little bit, I know the amplitude of sine of x is 1. I'm going to make the max appear 4 units high. And the min 4 units down below is -1. So we know sine of x goes to 0, 0. At pi over 2, it's 1. At pi, it's 0. At 3 pi over 2, it's negative 1. Okay, so let's draw our curve. Okay, and I'd like you guys right now to find for me what is the subinterval length, given that they want 6 subintervals, so that's n. A is 0, B is 3 pi over 2. What is my subinterval length? Yes, excellent. So we can look at it just visually speaking, or if you guys want to tie it to a formula, b minus a over n, which simplifies to 3 pi over 2 divided by 6. Same thing as 3 pi over 2 times the 6. So the 3 goes into 6 twice, and I have my subinterval length is pi over 4. So left Riemann sum means that pi over 4 is still the width. So this is the width. And now I'm coming with the height of each one of those rectangles. And the height this time is, if you look at 0 to pi over 4, the left of that subinterval is 0. So I'm going to start with 0. And remember that you guys are doing f of 0. You want the y value at 0. And then keep going because it's pi over 4 units apart. So f of pi over 4 plus f of 1 pi over 4, 2 pi over 4 is pi over 2, 3 pi over 4. And I'm supposed to end up with 6 rectangles. So I know I keep just counting up by pi's over 4 until I have 6. And right now I have 1, 2, 3, 4, 5. That's 4 pi over 4. So the next one would be 5 pi over 4. Okay, so f of 0 is the y value at 0. So if I plug sine of 0 in, I am going to say that if it requires unit circle values, that you guys evaluate that. It's not considered algebraic if it's a trig unit circle type thing. So you do have to come up with those values, but you don't have to simplify the rest of the way. So for example, sine of 0 is 0. Sine of pi over 4 is rad 2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4, second quadrant, sine is positive, so rad 2 over 2. Sine of pi is 0. And then sine of 5 pi over 4, third quadrant, sine is negative there, so minus root 2 over 2. And we can leave our answer like that. Okay, so that part of it, you don't have to simplify further because that's considered algebra. If it's trig, you do it. Okay, so it says, notice that it would be way more accurate if we use 10 rectangles instead of 6. But it would take a lot more work, which is true. Okay, so I'm going to end on the next page with an idea to kind of bring us back around from the PVA problems to the problems that we have now. So there was a part on the Dixie-Ross worksheet that I know you guys couldn't answer because it's part of this unit. So I'm going to just give a really basic example. If we have a velocity function and time, and I think of traveling on the 405 freeway on a wonderful day where there's no traffic and I'm just taking my time traveling 60 miles per hour. So that is a constant rate of change of 60 miles per hour. So I'm going to go ahead and just draw a horizontal line and say that this is 60 miles per hour. Okay, that's my velocity curve. It's a constant rate of change. And then I asked you, well, how far have you traveled after 2 hours? And you tell me, well, I would just take 60 miles per hour. So think science, and times it by the number of hours that I've traveled, so 2 hours, where the hours cancel out and my units of measure, I therefore can conclude that I've traveled 120 miles. So looking at your graph, if you guys go back to your graph, 60 miles per hour is a constant rate of change. And then you have, after 2 hours, we have 120. The physical representation of that is, well, isn't that just the area underneath that curve? And so I don't know if that blows anyone's minds, but the area underneath the curve of a rate of change function velocity ends up being the accumulation of distance. In this case, 60 miles per hour times the 2 hours leads me to conclude that I've accumulated over 120 miles during that time span. Okay, and so area underneath the curve, Riemann sum, we're still working on that idea of linking that together and then eventually tying that in with integration. So below here, the last class, before they left, I just had them plot this for me so that we can start off with that, is sometimes instead of giving you guys equations like we had above, like f of x equals that and f of x equals that they give you guys instead a table of values. So with that, if you guys can end the class and you can leave after you guys are done, just doing a simple plot for me where this is velocity and this is time. And the easiest way to do that, 0 to 3, if you guys can just parse it off by a half unit on your x. And then on velocity, I see that it starts at 0 and it ends at 20. So just a real rough sketch of your curve. Can you guys go ahead and go up to 20? And then plot your points. Just do a dot plot of what you guys have here. Oh my gosh, I counted wrong, you guys.